Welcome. So this is the second video in Chapter 6, which looks at the Solow model and tries to help explain how and why economies grow in the long run. The first video was a basic rundown of really the motivation and intuitions behind this Solow model and why we really care about it. This video focuses more specifically on the model itself and understanding the really basic mechanics and the basic lay of the land, so to speak. So The Solow model, again, focuses on capital accumulation as a source of economic growth. So in particular, the idea is that we're trying to understand how and why economies grow over time, in particular, how and why economies increase standard of living, their output per worker over time. And so if you recall, we transformed our production function into this, use a color here so you can see it, into this per worker production function. And so in this framework here, again, we're assuming that the labor force and technology are assumed exogenous. So we just take those as given, they just drop from the sky, okay? Now in the past we've used the term fixed, but it's not fixed in the sense that it never changes. It's fixed in the sense that it's just predetermined and it's something that this model is not trying to explain. It just comes from the outside and is dropped in our lap. So as a preview to what we're going to look at in the next two videos, in fact, are, again, to explain standard of living and what that means. And in the Solow model, what we will be able to see is that countries that have a higher have a higher saving rate are going to end up having a higher standard of living. Again, the basic intuition is that if countries have a higher saving rate, they're going to accumulate more capital. And that means for a given set of other inputs, they're going to be able to produce more output, and therefore output per worker is going to be higher. And so that would lead to a better standard of living. The second thing, the main result that we'll see is that countries that have higher population growths are going to dilute the capital stock, and that's going to turn out to reduce the amount of capital per worker and hence output per worker. And as I mentioned in the previous video, the limitations to this basic Solow model framework is that it doesn't allow us to explain sustained growth in output per worker over time. And we'll see an example of that at the end of this video. But more generally, it can't explain, it has a poor job of explaining cross-country variation in economic growth. And in particular, the fact that total factor productivity varies across different countries is an important source of variation in growth. This basic framework assumes that technology is essentially the same or exogenous, and so it doesn't do a good job of explaining cross-country variation in growth in that sense. So as I said, this basic Solow model framework focuses on the role of capital accumulation, and so the basic underlying fundamental is to try to understand how does the capital stock grow and why. And so to understand that, there's two basic things that are going to affect the capital stock. Now, from here on out, when I talk about capital stock, I'm really talking about capital per worker, okay? And so the analogous output, in terms of thinking about output, and the analogy is that we're really thinking about output per worker and the standard of living. So getting back to the capital stock, there's two things that affect capital stock. First of all, investment in new capital. So if, as we buy more capital, the capital stock is going to rise, ceteris paribus, okay? And so that's going to have the result of increasing capital per worker. But then we know that machines wear out, machines become obsolete, and so depreciation of the existing capital stock is actually going to have the effect of reducing the total amount of capital over time. And so those things, as we'll see, there's going to be a tension between those things in this particular model, which is going to actually help us explain this capital accumulation story. So it turns out when we have investment exactly equal to depreciation, then the capital stock is going to remain constant, and what we'll see is that that's going to characterize what's referred to as a steady state in this model. If we have investment greater than depreciation, that means that we're adding to the capital stock more than what's being drained away by this depreciation factor. So over time, you would expect the capital stock to go up. And then finally, if investment is less than depreciation, you have the opposite effect. You're not putting in as much capital as is required to replace depreciated machines, out-of-date machines, and those kinds of things. So overall, the capital stock is going to fall under those conditions. So we're going to set up a really basic economy. And so the amount of output, again, this is output per worker, is going to be equal to consumption per worker plus investment per worker. So this looks a little familiar because it looks a lot like the national income accounting identity. That's exactly what it is, but it's in per worker standards. Now, we're also making two big assumptions here. First of all, we're assuming away the role of government in net exports. Again, in the U.S. anyway, government expenditures has been a pretty constant percentage of total GDP over time, and so that's really not going to be a factor in terms of explaining capital accumulation in this model. And so we don't have to worry about the role of government in that case. Likewise, with net exports, it's a relatively small part of total GDP, so it's really not going to be a central part of understanding the story of capital accumulation over long periods of time. And so in this very simplified model, our GDP in terms of output per capita or output per worker is just generated by consumption goods and investment goods. So with this, the total amount of savings per worker can simply be expressed as Y minus C. So workers earn an income Y, they spend some of it on consumption goods, whatever's left over is saving, so little y minus C is the total amount of saving in the economy per worker. And that's going to be equivalent to this expression here, little s times little y. So here the little s is the saving rate. And so if we multiply the saving rate times the total amount of income per person, that's going to represent the total amount of saving per person in the economy. And so if households' choice is to save or consume, whatever they don't save, they consume and vice versa, it's got to be the case, and an implication of that is that we can express the amount of consumption by households as simply 1 minus the savings rate times output per worker. So we can use these definitions to understand the equilibrium for the economy. And so, as I said, our national income accounting identity means that output is equal consumption plus investment per worker. We can rearrange that in terms of our goods market equilibrium, which says that saving is equal to investment per worker, right? The total amount of savings is equal to investment per worker. Savings per worker is equal to investment per worker, rather. And we know that savings per worker is given by that expression that I just mentioned there, okay? Oops. So the punchline again is that this is really representative of a goods market equilibrium in the spirit of what we talked about in Chapter 4, where we have this goods market equilibrium between saving and investment. So let's look a little bit closer at the goods market equilibrium. Again, that's that expression there. And if we recall the production function in per worker terms, y is equal to a times k to the 0.3, we can put these things together to understand our goods market equilibrium. Here, that's total savings per worker, which is equal to the savings rate times little y, and little y is that expression there, okay? So this whole thing is what we're going to refer to as our investment function. This tells us how much we invest in new capital equipment. And again, the basic idea is that, well, we have some capital stock that we invest in that helps us produce output. So when we produce output, a fraction of that output we save, that savings gets channeled through financial markets into borrowing by firms, which then use those borrowings to increase the capital stock. And so that's how we can think about that investment function and the relationship that it has to the left-hand side. So ultimately, this is going to be telling us what's going to be increased in the capital stock. And you can see that it's sort of endogenous in the sense that a higher capital stock is going to lead to higher production, which means higher savings, and therefore channeled through financial markets is going to lead to higher investment over time. Okay. What about declines in the capital stock? Well, that's where the depreciation comes in. So we're going to assume that the capital stock depreciates at a constant rate delta, so the Greek letter delta. And so what that means is that every period we have an existing capital stock, and the fraction delta of that is just going to disappear. It's going to become obsolete, or it's going to wear out. It's no longer usable. And so what that means then is that the total decrease in capital per worker over time, or at any given period, is going to be delta times little k. And so that's going to be the decrease, that's going to represent the downward force on our capital stock. So if we put these two factors together, the things that increase the capital stock and the things that decrease the capital stock, that gives us this capital accumulation equation. Delta K, the change in the capital stock, is just given by how much we're investing in new capital versus how much is being is pulling the capital stock down through this natural process of depreciation. So let's look a little bit more carefully at this and go through a couple key cases. So if investment ends up being greater than depreciation, then it's pretty easy to see that there's our investment, right? There's our depreciation. And so what that means is that you're going to be building up the capital stock. You're putting in more investment in new capital equipment than what's being drained away through the depreciation process. So overall, the net effect on capital is that capital is going to rise over time. So as long as investment is greater than depreciation, you would expect an increase in capital over time. The flip side, if we have investment less than depreciation, pardon me, if we have investment less than depreciation, you have the opposite. So you're not putting in enough investment in new capital equipment to offset the effects of capital being obsolete and being worn away. So the net effect is that after this process, you're going to have less capital than what you started with. You're not replacing the depreciating equipment fast enough. So the net effect is that the capital stock is going to fall over time. And then finally, if we have investment exactly equal to depreciation, then there's our investment that's exactly equal to depreciation. So not surprisingly, the capital stock is going to remain constant. And so the change in the capital stock is going to be equal to zero. And so that plays a special role in this model, as we'll see. This is going to characterize what's referred to as the steady state. As we'll see in the model, once we get to this steady state, once we get to that position where the capital stock doesn't grow anymore, we're just going to sort of sit there. Excuse me. So when we put all of these pieces together, graphically, this is what the picture looks like. So let's start off with the depreciation line. So as we said, if we assume a certain capital stock, and we assume a certain level of depreciation per period, then this depreciation line is just going to be a linear equation that comes out of the origin. And so as the capital stock goes up, the total amount of capital that's depreciated over time is just going to be a linear function of that. And so I don't want to mess up this diagram too much, but you can see again, as the capital stock goes up, the total amount of depreciation that occurs is going to just be a linear line. Okay. Again, now you'll notice, I probably should have started off by mentioning this. We're measuring on the horizontal axis the amount of capital per worker, right? So that's the thing that we're really focusing on and trying to understand what drives capital per worker. And so we're going to measure on the vertical axis a bunch of different things that are going to be the outcomes of the capital stock: investment, depreciation. As we'll see in a second, we can measure consumption and also output per worker on the vertical axis. So I just talked about depreciation. The other factor, the other important piece here is investment. And so with this investment function, as I said before, given a certain capital stock, and we put that together with our production process, that determines total output. We save a certain... Okay, so we had a little bit of a technical glitch, so we're picking up right where we left off. And so we were talking about what this Solow model looks like. Now, again, we have this depreciation line, which is just a linear equation. It comes out of the origin. As capital stock rises, the total amount of depreciated capital goes up at a linear rate. And then we have this investment function, which is looks a lot like a production function, and there's very good reason for it. There's y right there, and we just multiply our production function y times the savings rate. And so if we wanted to, we could actually draw our total production function up here somewhere, okay? And so the basic idea is as we increase the amount of capital stock, that's going to lead to more production. Higher production is going to lead to higher savings. Higher savings means we're going to loan more money out in financial markets, and that's going to lead to higher capital overall. And so that's why we get this investment function that is upward sloping. Now, again, you'll notice it's increasing at a decreasing rate. That's because the production function, which is underlying this investment function, also increases at a decreasing rate. The steady state, as it turns out, is where those two things cross, where the investment function crosses the depreciation line. As we mentioned before, when investment and depreciation are equal, the capital stock is going to remain constant. And so that's the key fundamental of this, and that's where our steady state is going to be. As it turns out, if the amount of capital is greater than the steady state level of capital, we're going to be depreciating more capital than what we're putting into new capital. So overall, the capital stock is going to fall until we hit the steady state. Likewise, if we're at a level of capital like K1, the amount of investment we have is going to be greater than the amount of depreciation we have. And so as long as that gap persists between investment being greater than depreciation, you're going to grow the capital stock over time. And so that would suggest that capital is going to grow over time until we get to the steady state. And so once we get to the steady state, we're not going to, there's going to be no there's going to be no incentive or any sort of way in which the economy is going to move away from that unless something fundamental changes with savings rates or something like that. And so if we expand this diagram a little bit, again, this gives us a broader view of thinking about how all these pieces come together. I just discussed what happens when we're not at the steady state. So through these natural forces, the capital stock is going to rise or fall if there's a disconnect between investment and depreciation, and that's naturally going to push the economy towards this steady state equilibrium level of capital K star. Okay. Now, you can see that we've added in this diagram here our production function. So as the capital stock rises, you can see that investment is going to go up over time, and of course, output is also going to rise over time as well. And so if we figure out what the steady state level of output is at the steady state level of capital, we just read right off of our production function, and that's gives us our level of output. Again, this is output per worker or per capita. So that output that we're drawing there is essentially thinking that's our proxy for our standard of living. And so what this tells us then is that at this steady state level of capital, our steady state level of output per worker or standard of living is just equal to Y star. And finally, an important thing to note in this diagram is we can measure consumption. If you recall, consumption is just the difference between total income per person and investment, right? So we have Y is equal to C plus I. So if that's true, it's got to be the case that total consumption per worker is just equal to income minus investment. So this gap between our consumption function, our production function and the investment function here, that gap represents the amount of consumption at any given level of capital. Okay, so I want to summarize a few of the things that we've talked about here and in particular focus on the steady state. So the idea here is that in the steady state, the capital stock is not going to grow at all. It's going to be held constant. And so the change in the capital stock over time is going to be equal to zero. And the only way that that happens, of course, is if investment is equal to depreciation. And so that occurs where this investment line intersects the depreciation line. If the level of capital is less than the steady state level of capital, then in that case, we're going to be to the left of that steady state. And so what that means is that the total amount of investment that we're putting into new capital is going to be greater than the amount that's being depreciated away. And so overall, the change in the capital stock is going to be positive. So in other words, the net effect is we're going to grow the capital stock over time. And the capital stock is going to continue to grow until we reach that steady state level of capital. Once we get to that steady state level of capital, as we just saw, then we just stop. We end up at that K star level of steady state capital and the associated level of output per person Y star, and then we just stop growing. And so at that point, output per capita growth is equal to 0, which, as I pointed out before, is one of the flaws in this basic model. Oops. And then finally, if capital stock is greater than the steady state level of capital, you're going to have the opposite effect. So the amount of total capital depreciation is going to be greater than what you're putting in to replace new capital equipment. So overall, the net effect on capital is for capital to fall. Investment is less than depreciation. So the change in the capital stock is negative, capital stock falls. Over time, capital is going to decline until it hits that steady state level of capital. And at that point, ceteris paribus, we're going to sit there forever. And so we're going to just stay at that capital stock. And so at that steady state, as I said, capital and output per worker are constant and they don't grow. And as I mentioned before, we can measure consumption as just the distance between output per person and investment per person. So there's a few takeaways to this, which I'm going to expand on and in the next video. The first is that countries with similar savings and population and technology characteristics, so in other words, holding savings and population growth and TFP constant across these countries, what this means is that these countries will should eventually enjoy the same standard of living. If we start off at different places on that same diagram, we're all going to move towards K star, the same K star. That's what that means. And so really what the implication is that countries with differing levels of capital to begin with, but similar characteristics otherwise, the lower level of capital countries, that is the poorer countries, should catch up to the rich countries and eventually will enjoy the same standard of living. And so this is really what's referred to as the convergence theory, the idea that poor countries can basically accumulate capital to the point where they catch up to rich countries who are just sort of stuck at that same steady state. And so it turns out the evidence on convergence holding is somewhat mixed, and you can look at the book for that. And so, as I mentioned, the underlying factors, if all of those things remain constant, then eventually growth and output per person is just going to halt. It's going to go to 0, and then we're just going to sit there. And so that happens through this capital accumulation process where we reach the steady state. And so the important thing to underscore here is the limitation of this model in the sense that it doesn't allow us to explain sustained growth over long periods of time. If we look at growth in the US and many other countries, we've had sustained growth over time. We don't just stop and sit there forever. And so that's a limitation in this basic framework. So I want to do one thing, which is switch to the smartboard, and I can illustrate this basic convergence theory. Okay. So the basic idea of this convergence theory is you could have two countries, A and B, countries A and B. So you can see country B here, they're already at the steady state. Again, recall the steady state is where depreciation intersects with investment. So once we get to that steady state level of capital, we just sit there, and the level of output at that steady state level of capital is equal to Y star. So you can imagine situations where countries might have otherwise similar savings rates, similar technological factors, and similar depreciation rates. So if it boils down to those three factors and countries are similar, then you would expect this model to hold, at least in a basic sense. And so you can imagine a situation where country A is sitting here. they're starting out at a relatively low level of capital. And so what we know from these basic dynamics is that at the capital level K1, the amount of investment that goes on in the economy is greater than depreciation. And so what that means is there's going to be a net increase in capital over time. So as capital grows, this economy A is going to increase and accumulate more and more capital. And as it does that, you can see that not only the capital stock, but the amount of output per worker is going to rise over time. So hence you have growth in output per worker. You have an increased standard of living. But like we've just talked about, once country A gets to this K-star level, they're just going to stop there. And so what that means, again, is that in theory, if this convergence theory holds, then you can see country A catching up over time to country B in terms of enjoying the same standards of living as the higher, richer countries do. As I said, some of the evidence on this convergence theory holding is somewhat mixed. So that's all for now. I'm going to talk about what changes when some of these factors change in the Solow model, what the implications are for the steady state and how we interpret it with some of the data. Thank you.